Hello Year 12 and welcome to another lesson within the unit of quantum physics. Today's lesson will be about a very important topic, probably the most important topic within quantum physics, and it's a topic where quite a few of the exam questions do crop up for this unit on this particular topic. Today's lesson then is about the photoelectric effect. Okay, so what is the photoelectric effect? Let's give you an important definition to start with. So the photoelectric effect is when electromagnetic radiation of a particular frequency is shone on the surface of a metal, electrons are emitted from its surface. Okay, this phenomena is what we call the photoelectric effect, and the electrons that are released or ejected or emitted or liberated from the metal surface are called photoelectrons. We can demonstrate the photoelectric effect using a device called the Gold Leaf Electroscope. An electroscope is just a device which is used to detect electrical charge on a body. So this particular gold leaf electroscope consists of a stem that's usually made from copper, which is a conductor, sometimes brass, and to this we attach a thin gold leaf. There is a metal cap attached to the top of the stem, and on top of this cap we can place the metal that we want to irradiate with electromagnetic radiation. Okay. The metal cap is mounted on insulation. The cap is insulated from the copper or the brass conductor stem. Okay. If there is no charge present on the cap of the gold leaf electroscope, then the gold leaf will be in a fully collapsed position. Okay, we'll look at this in a little bit more detail. It's also important to remember that within this glass case is a vacuum, because the last thing we want is any wind causing the gold leaf to flap about. Okay. So let's try and understand how the gold leaf electroscope can be used and how it works. So for example, if we brought a negatively charged rod made, let's say, of polythene, and we bring it and touch it or rub it onto the cap, okay, remember it's negatively charged, the excess electrons on the negatively charged rod will flow down due to conduction through the copper conductor, get accumulated onto the gold leaf. As a result, the gold leaf diverges due to repulsion between the negative accumulated charge on the copper conductor and the gold leaf itself. So now let's imagine that instead of having a negatively charged rod, we have a positively charged rod. This could be, for example, perspex. If we rubbed a cloth onto perspex, we will take off some of the electrons from the perspex that will fall onto the cloth, and that leaves the perspex rod positively charged. So if we brought a positively charged rod, okay, and touched it on the metal cap, the electrons from the gold leaf travel up through the conductor and reach the rod as a result of conduction. This is then causing a deficiency of electrons in the gold leaf, leaving it positively charged by and large, and basically those positive charges are accumulated in the gold leaf, causing the like charges of the gold leaf to repel away from the like charges of the, let's say, copper conductor stem. Okay, so the electrons ultimately are flowing up and are attracted to the positive rod at the top. Okay, and this causes also divergence of the leaf as well. Okay, so it's not in a collapsed position, but it sort of stands upright. Okay. Now, we can also use the Gold Leaf Electroscope to find the presence of charge on a body by the principle of electrostatic induction. So this is different to actually bringing the rod and touching it onto the metal cap. So what we do here is we are not touching the body or the rod with the cap. So if we start off with a picture on the left-hand side, and we bring the positively charged rod just near the cap, it attracts the negative charges from the gold leaf, and they flow up and get accumulated on the cap, leaving behind positive charges, as there is now a deficiency of electrons at the gold leaf. This causes the gold leaf to diverge from the copper conductor. Similarly, as we look to the picture on the right-hand side, if we brought a negatively charged rod close or near to the metal cap, it repels the electrons that are present in the cap. They travel down through the conductor and accumulate themselves at the gold leaf, leaving behind positive charges on the cap. The negative charge accumulated at the gold leaf causes it to diverge as well away from the copper stem, which is also now negatively charged, okay, because of all the positive charge that is accumulated at the top. The important thing to remember here is the electrons are not or protons are not actually transferred from one object to the other because they're not in contact, but we just see a movement of the electrons so that they are attracted towards or repelled away from the rod, depending on what the charge is on the rod itself. Okay. Now, I just want to recap on this to make it clear. I have touched on it. Just want to make it clear that you can make a polythene or a PVC rod negatively charged by rubbing it with a woolen or a silk dry cloth, which transfers electrons from the cloth to the PVC or the polythene rod, as shown in the diagram. Okay, that gives the polythene or PVC rod an overall negative charge. Now, just also to be clear that if you had a perspex rod, which is sort of a rod that looks like a clear plastic, okay, and you did the same thing, you rubbed a cloth on it, a woolen cloth, okay, what you find in this case is that you strip off electrons from the perspex rod, leaving it with an overall positive charge. So if you're having a perspex rod and you rub it, just remember that you will leave it positively charged. If you do the same thing with a polythene or a PVC rod, you leave it negatively charged. Okay. Now, just want to again also recap to make it clear that when you actually touch the charged rod onto the metal cap or plate of an electroscope, as shown in this diagram, you transfer the negative charge from the PVC rod to the electroscope. Okay, once they make contact, some of those electrons from the PVC rod end up onto the electroscope plate and further down. So touching causes the actual transfer of electrons from the PVC to the electroscope cap, as opposed to if you were just doing induction, where you would just repel the electrons that are already in the electroscope further down the bottom. But here we actually get a transfer of electrons from one body to the other. This makes the gold leaf repel from the negatively charged copper stem, as both the stem and the gold leaf have the same charge. Okay. Now, since the electroscope has acquired an overall negative charge, this will spread out throughout the entire electroscope, this negative charge. Okay. Now, with induction, it's a little bit different, electrostatic induction. Okay, that is where the same charged rod, let's say it's a polythene rod, doesn't come into contact with the electroscope. Okay, we just bring it close by. So let's assume we have a negatively charged rod as in this diagram, causing electrons to be repelled down the scope. Okay, no transfer taking place here of electrons from one body to the other. It's just a repulsion of these electrons. When I take the rod away, okay, as shown in this next diagram, they return to their original position. Okay, all of these electrons spreading out evenly throughout the electroscope, and therefore the leaf falls back down. Okay, so it's not this is all very temporary as long as you've got the charged body close by. As soon as you take away the charged body, then the gold leaf will return to its original position. Okay. Now, touching the negative rod, again, remember, causes some electrons to transfer over to the electroscope, causing a buildup of negative charge at the leaf, which is then causing it to stay repelled. Okay, so that's if it's touching, that's permanent. Okay, but when it's induction like this, as soon as you take the rod away, it's not permanent any longer. Okay, now what would happen if I touched my finger on the electroscope cap as shown in this diagram? Okay, well, remember my body is now connected to the ground. Okay, so when the negatively charged electroscope is touched in its way, its charge becomes grounded or neutralized. The grounding process involves a transfer of electrons between the charged electroscope to the ground, okay, in this case. So the electrons leave the electroscope to go to the ground, causing the gold leaf to go back to its naturally fallen position. If the scope was positively charged, electrons would travel from the ground through me and into the electroscope, neutralizing it and causing the leaf to also fall back to normal. Okay. So we've seen two methods of charging an electroscope, by contact or by electrostatic induction. Okay, so just remember that the method using a contact, as soon as you take away the charged body from the electroscope, what you find is that it's a little bit more permanent because the gold leaf remains deflected. Whereas when we're talking about electrostatic induction, what happens is that as soon as we remove the charged body away from the vicinity of the electroscope, the gold leaf falls back down, so it appears to be a much more temporary deflection of the gold leaf. But there is a way to make the electrostatic induction permanent, so that when you actually remove the charged body away from the gold leaf electroscope, the gold leaf actually does remain deflected. Okay, and so here is a picture of a gold leaf electroscope, and we'll show you through this PowerPoint slide how we can go about making the electrostatic induction permanent. So we bring the negatively charged PVC rod near the electroscope, and that causes the electrons in the electroscope to fall down towards the copper conductor or copper stem, which becomes negatively charged. So does the gold leaf as well. So both of them are negatively charged, so they will repel, causing the gold leaf to deflect. Okay, as shown in the diagram. So if I then bring my finger and touch the electroscope with my finger, it will discharge, okay, causing the gold leaf to fall back down to its natural position, okay. And then I bring the PVC rod nearby, and the gold leaf doesn't move at all, as I have a lower resistance path for those electrons that are being repelled back to the ground through my finger, okay. If I remove my finger now, there is a deficit or shortage of electrons on the electroscope, so it's now positively charged. So when I remove the PVC rod, we see the net positive charge causing a deflection of the gold leaf. Now if you go back to picture 2, the electrons that are repelled by the negative charge on the PVC rod leave through my finger and go to ground, leaving this net positive charge on the electroscope. Then I remove my finger, as in picture 3, and we're left with the electroscope isolated from ground with a net overall positive charge. So now, when I remove the negatively charged PVC rod, as in picture number 4, the positive charge will redistribute and cause a deflection of the gold leaf. Okay, now this setup here is actually so when we're doing the photoelectric effect experiment with the electroscope, we can either do it by contact, or we can do it in this way, this permanent electrostatic induction method. Okay, so actually on this Gold Leaf Electroscope, a metal plate, which is usually zinc, is placed on top of the metal cap, as it is in this particular picture. It is negatively charged by touching it with a positively charged perspex rod, okay, using electrostatic induction. Okay, so we know that when this is done, the metal stem and gold leaf will also become negatively charged, so the stem and the leaf repel each other and we get this deflection. Okay, and then what we would do is we would bring a normal visible light lamp, a desk lamp, and a UV lamp, okay, that we will be shining on this metal plate that we have charged by electrostatic induction. Okay, and just very importantly, before we use this zinc plate, it is absolutely essential to give the plate a scrub on both sides with iron wool to remove the surface oxide layer. Okay, so we've got ourselves now a desk lamp and a UV lamp, and we're going to shine the desk lamp or the visible light onto the plate that has been given this negative charge. Okay, and we will also after that shine the UV lamp as well on this negatively charged plate. Okay, now we can do the same as well by making the zinc plate positively charged if we rub it if we rub or make contact using electrostatic induction by using a polythene rod as well. Okay, so we've managed to get our zinc plate positively charged by electrostatic induction. So when we shine a desk lamp, which is just a visible light incident on the positively charged zinc plate, we find that the gold leaf remains in its deflected position and doesn't move at all. Okay, now when we then shine a UV light from a UV source, okay, onto the positively charged zinc plate, again there is no movement of the gold leaf. Okay, if we then shine visible light again, but this time on the negatively charged zinc plate, this also causes no movement of the gold leaf. Okay, no matter how bright or how long it shines for, or how intense the visible light beam is. However, when UV light, okay, is shone on the negatively charged zinc plate, the gold leaf falls back down to its natural position. This means that the UV light must somehow be discharging the electroscope. We started with negative charges on the plate, okay, so the UV light must have somehow been releasing the electrons. The metal plate is losing its negative charge through the emission of electrons, which are repelled by the negative charge on the electroscope. So the discharge of the electroscope cannot be caused by ions in the air, as the electroscope is in a sealed vacuum. So it must be something else. Now, there were some very key observations from the photoelectric effect that you need to be familiar with. And these observations blew lots and lots of holes in the wave theory or wave model of electromagnetic radiation. Okay, so here was the first observation. Photoelectrons were emitted only if the incident radiation was above a certain frequency, the threshold frequency F0 for that particular metal. No matter how intense or bright the incident radiation, no single electron would be emitted if below the threshold frequency. Okay, so the electrons will be emitted from the surface of a metal only if the incident radiation is above a minimum frequency called the threshold frequency. This is determined by the metal itself and is different for different metals. Below the threshold frequency, no electrons are emitted. Now, wave theory suggested that low frequency light should work, and it would just mean that electrons are released more slowly, but that just wasn't the case. The second observation was that if the incident radiation was above the threshold frequency, then emission of photoelectrons was instantaneous. So the emission of electrons started the moment the surface started to be irradiated, or as soon as light shone on the metal, provided that the incident radiation exceeded the threshold frequency. Now, according to the wave model, very intense light should be needed to have immediate effect. Their observations showed that even weak or low intensity light was effective. According to the wave model, weak light waves should have no effect. Now, that wasn't the case. Increasing the frequency of light, according to the observations, increased the maximum kinetic energy of the electrons emitted. Now, again, wave theory suggested that it should be the increasing intensity or amplitude and not the frequency that increases energy of the electrons. Okay, so that one also didn't work out too well. The final important observation was that if the incident radiation was greater than F0, the threshold frequency, then increasing the intensity of the radiation didn't increase the maximum kinetic energy of the electrons. Instead, more electrons were emitted by the increasing intensity of the radiation. The only way to increase the maximum kinetic energy of those photoelectrons was to increase the frequency of the incident radiation. So increasing the intensity of the light increases the rate at which electrons leave the metal. Now, wave theory suggested that the greater the intensity, the electrons emitted should really have more energy, but that's not the case. The energy is the same. Now, according to the wave model, if we had lots and lots of visible light, all the wavelengths should combine together and in total give us enough energy to get rid of these electrons, but it just didn't happen. If the wave model worked, then we should see electrons liberated with any frequency of light, so long as the light was bright enough. But again, that wasn't the case. If light just acted like a wave, we'd have a brighter light and more waves coming in. The wave model expects that these waves be absorbed by the electrons, and the electrons get the energy from the light and they would be liberated. But we didn't see that happening at all in the photoelectric effect experiment. As an example, if the threshold frequency for a particular metal is in the green part of the visible spectrum, bright red light doesn't cause emission of electrons. Red light has a lower frequency than the threshold frequency for this metal, yet very dim blue light would cause emission of electrons. Again, this didn't fit with the wave model, in which the rate of energy transferred by the radiation is dependent on its brightness. The more intense the radiation, the more energy is transferred to the metal per second, and the bright red light transfers more energy per second than the dim blue light. So how could weak ultraviolet waves be more effective than the intense invisible light causing electrons to escape? So again, we had another hole in the wave model. Now, the photoelectric effect phenomena clearly couldn't be explained by using the wave model of light. So Einstein came along and made his proposals. But before we talk about the proposals that Einstein came up with in order to explain the experiment of the photoelectric effect, let us just make sure that we can define threshold frequency. We've been talking about it a lot in the previous slide, and sometimes this will come up as a one-mark question. So the threshold frequency, F0, is the lowest frequency of radiation that will result in the emission of electrons from a particular metal surface. Now, for most metals, this frequency, threshold frequency, occurs in the ultraviolet region of the electromagnetic spectrum. So the photoelectric effect phenomena can't be explained using the wave model of light. but it can be understood if we adopt the idea that radiation arrives at the plate, the zinc plate in this case, as packets of energy called quanta or photons. Okay, so in 1905, Einstein suggested that the incident radiation was not behaving as a wave, but as packets of energy that arrive with fixed or discrete energy values depending on the frequency of the light. These packets of energy are called photons. Okay, it's the frequency of light that makes the big difference. Okay, that's the key. And it took the genius of Einstein to explain what was going on, and it was for this work that he was awarded the Nobel Prize some years later in 1921. Now, a single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Okay, so in this picture, for example, we have visible light in the form of red light photons that are arriving with not enough energy and not enough frequency, so frequency below the threshold frequency, and are unable to therefore liberate any electrons whatsoever. Whereas on the picture on the right, we have ultraviolet photons arriving, and each ultraviolet photon has more higher frequency than the threshold frequency, and so each one is able to liberate one specific electron. So there's a one-to-one interaction going on. Okay. Now, the incident radiation of the photons must exceed the threshold frequency for a particular metal. This is needed to provide at least the minimum energy required to release an electron from the surface. Now, this minimum energy is called the work function, and this is another important definition, and it has the Greek symbol phi. The work function phi is the minimum amount of energy required to release an electron from its surface, overcoming the electrostatic attraction between the electron and the positive metal ions. Okay. Now, metals such as zinc, which is the one that we've been looking at in the photoelectric effect experiment, they have electrons that are not very tightly held within the metal. We know that these are called the conduction electrons, and they're free to move about in the metal. When photons of electromagnetic radiation strike the metal, some electrons break free from the metal surface. They only need a small amount and a certain amount of energy to escape from the metal, which is about approximately 10 to the power minus 9 joules. Now, each photon could transfer its exact energy to one surface electron in what we call a one-to-one interaction. Now, since the energy of a photon is dependent on its frequency, if the frequency of the photon is too low, the intensity of the light or the number of photons per second doesn't matter, as one photon delivers its energy to a single surface electron in that one-to-one interaction. If the photon doesn't carry enough energy on its own to liberate an electron, the number of photons makes no difference, as its frequency is just too low. If the frequency is above the threshold frequency for the metal, then each individual photon has enough energy to free a single surface electron, and so photoelectrons are indeed emitted. Now, electrons cannot accumulate energy from multiple photons. Only one-to-one interactions are possible between photons and the photoelectrons. Okay, now here, let's just picture the electrons as being trapped in an energy well as shown in this diagram. Okay, a single electron requires a minimum energy phi, which is the work function, to escape the surface of the metal. Now, the work function energy, which we also call the work function, is the minimum amount of energy required to escape its surface. So electrons are attracted by the electrostatic forces due to the positive metal ions. Okay, a single photon could provide the energy needed by an individual electron to escape. The photon energy would need to be at least as great as phi, the work function. A photon of visible light has less energy than the work function, so it cannot release an electron from the surface of zinc. Now, when a photon arrives at the metal plate, it may be captured by the electron, and the electron gains all of the photon's energy, and the photon's energy no longer exists. Now, some of the energy is needed for the electron to escape from the energy well. The rest is just the electron's kinetic energy. Okay. Now, each packet of energy is able to release an electron, one electron, from the metal. Okay. Now, just to get you a bit more familiar with potential well diagrams, okay, here is another diagram, and that shows low energy, low frequency red light, which is shining on a photosensitive surface. The low energy photons of red light are unable to eject photoelectrons from the surface, okay, because the energy is a lot less than the work function. Okay. Now, the medium energy photons of green light can raise the electrons to the surface of the metal, as you can see, but not give it enough energy to escape. However, the high frequency violet light photons give the electron sufficient energy for it to escape from the surface, with some remaining kinetic energy as well on top of that. Okay. Now, increasing the intensity of the incident radiation of photons only increases a greater rate of emission of photoelectrons, but none of the emitted photoelectrons will ever move faster. The only way to increase the maximum kinetic energy of the emitted photoelectrons is to increase the frequency of radiation. In that case, increasing the frequency means each photon has more energy, and so each electron has more kinetic energy after it has been freed from the metal that has its specific work function to overcome. So on the left we have photons of blue light, okay, and then we increase the frequency, okay, from blue to UV, okay, and this increases the kinetic energy of the emitted photoelectrons, as we can see by the arrows that are showing them traveling at greater speeds with greater amounts of kinetic energy. So the kinetic energy of each photoelectron depends on how much energy was left over after the electron was freed from the metal surface. Okay, at a given frequency, all photons have the same amount of energy and the metal a specific work function. So there is a maximum value of kinetic energy that any emitted photoelectrons can have. Now we've come to the end of the first part of the photoelectric effect lesson. So I would like you to have a go at question number 1 to 5 and see how you get on. Okay, so pause the video at this point and try these 5 questions. So, how did you get on with those 5 questions? Here are the answers, and they are broken down into the individual marks as well. Okay, so at this point you can have a little break, and after this we will continue with the photoelectric effect and look at the photoelectric effect equation developed by Einstein. So in his model of the photoelectric effect, Einstein applied the idea of the conservation of energy to the photons and photoelectrons. Okay, so he was able to say 2 important things about what the energy does. The first one is that it frees a single electron from the surface of a metal in a one-to-one interaction, which we talked about before. And secondly, any remainder is transferred into the kinetic energy of the photoelectron once basically the work function has been overcome. Okay. So Einstein created the photoelectric effect equation using the conservation of energy and this photoelectric experiment results. And these photoelectric effect experimental results showed him that the electrons released had a range of energies for a given metal and incident radiation, up to some maximum value called the KEmax, or kinetic energy max. These fastest moving electrons, okay, yielding the highest kinetic energy, are the ones which were least tightly held in the metal, and so were the easiest to free from the electrostatic attraction between the metal ions and the electrons. Now, imagine a single photon interacting with a single surface electron and freeing it. Now, according to Einstein, the energy of a photon, E photon, is equal to the work function, okay, plus the maximum kinetic energy of the electron. And these are for the surface electrons, okay? These are the easiest ones to set free or liberate from the metal surface, okay? So the energy of a single photon is equal to the minimum energy required to free a single electron from the metal surface, which is called the work function, plus the maximum kinetic energy of the emitted electrons, the ones that are traveling the fastest, okay? And so we know that the energy of a single photon is hf, so we can write that there, which is equal to the work function plus KEmax, okay? Or we can also write this as the hf is equal to the work function phi plus a half mv squared max, okay? So why maximum kinetic energy? So let's take a look at our potential well diagram again. We start with a photon of energy E is equal to hf. This is represented by the ultraviolet radiation coming in. It is absorbed by the single electron. Some of the energy is used in escaping from the metal, and that is what we call the work function. The rest remains as kinetic energy of the electron. Okay, so some of the energy is needed for the electron to escape from the energy well, and the rest is the electron's kinetic energy. Now, that's one scenario, okay, but there is another scenario. What if the photon is absorbed by an electron that is lower in the energy well? Well, the electron will have less kinetic energy than the kinetic energy maximum. Okay, so the work function is the energy required to do work against the structure of the metal that the electron is a part of. An electron on the surface of the metal is the least tightly held one in the structure, as we've talked about already. It is bound to the metal by that energy, and to release it, you have to input that amount of energy. Each metal has a different structure, and so has been found to have a different work function. Those that hold onto their electrons lightly have a low work function, and those that hold on tightly to their electrons have a higher work function. The most loosely held electron, the one on the surface, which is shown on the left diagram, will have the most energy left over and will have the maximum value of kinetic energy. The others will have lower amounts of kinetic energy, as they will need more to escape. The maximum is there because electrons with the most energy left over for kinetic energy will be those on the surface, and those electrons a little deeper, as shown in the diagram on the right, will also escape, but they'll need to use more of the energy to do work against the metal's hold on them. So in reality, a range of energies will be observed. Okay, so a more tightly bound electron lower in the energy well will have less kinetic energy than the kinetic energy maximum, needing more energy to release it from the metal. If the photon strikes the surface of the metal at the actual threshold frequency F0 for the metal, then it will only have enough energy to free a surface electron, with none left over or no energy left over to be transferred into kinetic energy of the photoelectron. In other words, if the frequency of incident radiation has a value equal to the threshold frequency F0 of the metal, the kinetic energy of the electron is 0. So according to Einstein's photoelectric equation, that would leave us with HF0 is equal to phi, the work function, plus kinetic energy, which is 0, or simply HF0 is equal to the work function phi. Now, we can rearrange that equation, and we can also find that F0 is equal to the work function divided by Planck's constant h. Okay, so we can have an equation for the threshold frequency as well. So here we have our potential well diagram again. Now, if we have a quantum of radiation with an energy greater than the work function phi, or in other words, a frequency that is greater than F0, the threshold frequency, falling on the metal surface, then an electron will be emitted with some kinetic energy and escape the surface. The kinetic energy of the electron is just the difference between the energy of the quantum and the work function of the metal. We can express this in a slightly different way, whereby we know that the work function phi is also equal to HF0. Okay, and so if we rearrange our equation, the photoelectric effect equation that we originally had, we should make kinetic energy the subject of the equation, which is half mv squared, and the kinetic energy is given by the energy of the photon, hf, minus the work function energy, or work function, which is also given by hf0. So we can replace the phi work function symbol with hf0, where f0 is the threshold frequency, okay, for that particular metal. Now we can also plot a graph of the maximum kinetic energy against the incident frequency. We plot the maximum kinetic energy on the y-axis and the incident frequency of the radiation on the x-axis, okay, for a particular metal. And what we end up with is a straight line, okay. And we know that the equation of a straight line is y is equal to mx plus c, and we can rearrange our photoelectric equation so that it resembles the equation of a straight line. So kinetic energy maximum is simply the y value, and the frequency is on the x-axis, so that must be the x, and the gradient must be h, which is Planck's constant, and the y-intercept we can clearly see is the minus phi, okay, minus the work function. And this shaded area over here, which is to the left of the threshold frequency, which in this particular diagram is called Ft, we normally call it F0, but they've called it Ft. Everything to the left I've shaded in light brown, and that means that no photoelectrons are emitted when the frequency is less than F0 or Ft, okay? So below the threshold frequency. So if the incident radiation has a frequency less than the threshold frequency, the important thing to also note is that a single photon can still give up its energy to a single electron, but the electron, as we know, cannot escape from the attractive forces of the positive metal ions. The energy absorbed from the photons appears as kinetic energy of the electrons. Now, these electrons lose their kinetic energy to the metal ions when they collide with them. This warms up the metal, and that's why if you place a metal under a table lamp, it gets hot. Now, some electrons, in the metal are closer to the positive metal ions than others. Their relative positions affects how much energy is required to free them. The work function is, as we know, the minimum energy required to free an electron from the metal. Most electrons need a little more energy than the work function to free them. An electron that requires the minimum amount of energy to free it, i.e. the work function of the metal, would have the most energy left over from the incident photon. Now, it's important to be clear as well that only a few of the emitted photoelectrons have a maximum kinetic energy. Just a few. Most have a little less, so they would be traveling a little bit slower. So here is a summary table of the success of the photon model in explaining the photoelectric effect. Now this links to slide 10, so if you want to have a look at slide 10 again, you can do. I've talked about in slide 10 the observations of the photoelectric effect, and I've broken them down here into smaller chunks and written down what the wave model proposed about each of those observations and how they were all wrong, except for the third row, which proved to be the only part of the wave model that did explain the observations. All the other observations were just not able to be explained by the wave model. So Einstein proposed the photon model to explain each of these observations. I'll run through them with you. The emission of electrons happens as soon as light shines on the metal. Now, the wave model said that very intense light should be needed to have immediate effect, but that wasn't always the case, because if you had weak low intensity light, that was also effective as well to release photoelectrons. Now, the photon model for the emission of electrons happening as soon as light shines on the metal said that a single photon is enough to release one electron. So that's this one-to-one interaction. We can think of the electron as having an energy pouch, a container where it almost literally puts energy it collects in the form of photons. Now, this pouch can hold only one photon at a time. An electron cannot gain energy by absorbing two photons of energy. Some of the energy is used to liberate it from the atom. The remainder contributes to the electron's moving energy as a free particle. Now, the second observation is that even the weak or low intensity light is effective, but the wave model said that weak light waves should have no effect, and that was obviously not the case. So the photon model that Einstein proposed said that the low intensity light means fewer photons and not lower energy photons, just fewer number of photons. The third observation, increasing intensity of light increases the rate at which electrons leave the metal. This was the only part of the wave model that did explain this phenomena. The wave model said that the greater intensity means more energy, so more electrons are released. The photon model more or less said something fairly similar, that the greater intensity means more photons per second, so more electrons released per second. The fourth observation was that increasing intensity has no effect on energies of electrons. The wave model suggested that the greater intensity should mean electrons have more energy, but there was no link between the intensity and the energy of the photoelectrons released. The photon model proposed that the greater intensity does not mean more energetic photons, so electrons cannot have more energy. The fifth observation was that a minimum threshold frequency of light is needed. The wave model said that low frequency light should work. Electrons would be released more slowly, but that wasn't true. The photon model said that a photon in a low frequency light beam has energy that is too small to release an electron. Okay. The final observation was that increasing frequency of light increases the maximum kinetic energy of electrons. The wave model said that it should be increasing intensity or amplitude and not frequency that increases the energy of electrons, but that wasn't the case. So the photon model proposed that higher frequency means more energetic photons, so electrons gain more kinetic energy and can move faster. Changing the conditions of photoelectric emission. What do we mean by that? So let's take some examples. So let's imagine that we have this incident radiation and it is below the threshold frequency. It means the photons don't have enough energy to overcome the work function of the metal, resulting in no emissions of photoelectrons. So here, for example, is visible light. In particular, we're looking at red light, okay, and it's unable to cause the emission of photoelectrons. In this picture here, we are looking at green light, okay, in the visible part of the electromagnetic spectrum. The incident radiation here has a frequency that is equal to the threshold frequency, causing the electrons to be emitted from the metal surface, but with zero kinetic energy, okay. Now in this third picture we have blue light. The incident radiation is above the threshold frequency, causing electrons to be ejected with some kinetic energy from the metal surface. Increasing the frequency of radiation further increases the kinetic energy of the photoelectrons. Okay. Now over here we have the same frequency radiation as in the third diagram, but what we're doing here is we're increasing the incident intensity of the wave of a single frequency above the threshold frequency, and this means more electrons will be ejected per second, but it will not affect their kinetic energy. Okay. Let's take a look at a worked example, which is covering the topic where we have emitting photons from a metal surface. So the question is asking the following. Photoelectrons with a maximum kinetic energy of 9.34 times 10 to the power minus 34 joules are emitted from a metal with a work function of 2.40 electron volts. Calculate the frequency of the incident radiation. Now, we need to decide what is the correct equation we need to find the frequency of radiation, and that is HF is equal to phi plus KEmax. Now, the other thing that we need to consider is that we need to convert the work function into joules to maintain consistency of units, because we have at the moment the work function given in electron volts, but we have the kinetic energy of the photoelectrons given in joules. So to convert this work function into joules, we have to multiply by 1.6 times 10 to the power minus 19. So we multiply the work function in electron volts by 1.6 times 10 to the power minus 19, and that will give us our value of the work function in joules, which is 3.84 times 10 to the power minus 19 joules. Then we can substitute the values into the equation to calculate the energy of a single photon. So we have HF is equal to 3.84 times 10 to the power minus 19 plus 9.34 times 10 to the power minus 34, which gives us the energy of a single photon as 1.32 times 10 to the power minus 18 joules. Okay, then we can now rearrange our equation because we know Planck's constant and we know the value for the energy, so we can make F the subject of that equation, the frequency, and then we get 1.32 multiplied by 10 to the power minus 18, divided by Planck's constant, which is 6.63, times 10 to the power minus 34, and we get an answer of 1.99 times 10 to the power 15 Hertz. Now it's your turn to have a go at these questions, question numbers 10 to 13. There are some important constants that are given to you, such as the speed of light that you will need in a vacuum. Planck's constant is given to you as well. The mass of an electron is also given, and the elementary charge of an electron is provided as well. Okay, so have a go at those questions. Pause the video and see how you get on. Here are the answers to the questions number 1 to 13. How did you get on? So have a little look and see if you're working out and your answers match these. Okay, and then that will be the end of today's lesson. I hope that you did okay with this. It's quite a difficult topic compared to some of the others that we've done so far in this unit, but it's also one of the most important and one of the most interesting that pops up in the exams quite regularly.